what we're getting into today now, so we've done kind of basically the basics to get out of the way. We've done equilibrium, we figured out how to calculate forces in 3 dimensions and stuff like that. We've understood moments and rigid bodies and that sort of thing. Now, and then we went into centroids, which was kind of that little in-between, a sidestep there to figure out where that equivalent load's occurring. Because when we find out, when we do equilibrium, what we need is forces and to be able to break them up into x, y, and z components. So now that we've got kind of all of the main stuff out of the way, we get to do fun stuff. And this is actually, we're going to be doing truss analysis, which is something that you'll, civils tend to do a lot more of, but mechanicals also have to worry about it too from time to time. But this is basically looking at some of the early approaches for designing trusses and that sort of thing before finite elements and computers came along. But a lot of these methods basically are just going to be something we're going to be able to apply and actually start solving for basically ballpark figures. We're going to be able to look at what's going on internally now in a structure, in a particular element, and get an idea, okay, well, I need to size that bigger or smaller. Is it in compression? Things like if you have a truss element in compression, you got to worry about really not so much crushing, but buckling. And that'll be a whole separate issue you get into in junior, senior year. Tension, then you need to make sure you have enough area there so the thing doesn't snap and that sort of thing. So the cool thing, somebody hit the lights for a second there just so everybody can see. I'm not sure. Just the front ones if you got them or you have control over them. Oh, cool. Thank you. I went out gracefully and everything. Cool thing about trusses, though, is look around. You know, when you go into a Costco or something like that or some of the big stores, you'll see basically trusses holding up roofs. There's truss structures all over the place. Airports and that sort of thing, you'll find this is a 3-dimensional type truss there. But basically what we'll see, and we'll be talking about this a little bit there, but notice how it's connected. What do you think that is? It's a pin, yeah. And we know how to deal with pins, huh? How many forces? 1 force, 2 components. We'll get it yet. Yeah. It's going to be, partial credit. Yeah, we'll give you 2 points on that. Also, you're basically seeing this bridge in the stage that it was back in 1936 there. This is when they were building the truss structure there across the bay there, the east side bay out of Oakland to the, is that Treasure Island or? That's the one that's being phased out, and it's probably, they've dismantled it almost to this portion here, so it's actually, what you're seeing is probably what's out there today, except there's a nice suspension structure there hanging alongside of it and stuff too. But again, the key thing is we see a lot of things like that, bridges especially are going to be. In our houses, when we look up, we'll see basically truss structures holding up our roofs. Now again, look at this connection here. We'll talk a little bit about that. It doesn't look like a pin anymore, does it? It's basically kind of a gusset plate is what we call it. So basically it's a piece of metal, and they've put bolts through it and stuff like that. But they connected all the pieces together there through that gusset plate. Trusses were historically the way to get across streams and stuff like that, besides the arches and stuff. But trusses were kind of easier to do because when you look at it, when you think of a arch bridge and stuff like that, there's a lot of stone, there's a lot of material there. When you look at a truss structure, you're actually building something to cross a length with little material. It's not a whole lot of material there. Those are kind of thin pieces of metal there. They do them with wood and that sort of thing too. But the idea is, and the other key thing is note that none of these members these are all connected, but they're all relatively short compared to the span that they're crossing there. So it's nice in the sense that one of the key things that we like about trusses is we can compose it of a whole bunch of small members to cover a vast space. Oh, I went backwards. One thing I wanted to note here too, especially on bridges, you'll note that these are what we call through trusses, where basically the traffic, or in this particular case, the roadway goes through the truss. So it goes actually kind of into the truss and through it. But trusses don't always have to happen that way. They can be underneath too, with the roadway on top and stuff like that. But again, it's a truss structure that's holding that up. Again, a bunch of small elements there that they put together and across large expanses. This one kind of combines the truss structure with an arch too, which is kind of cool. Looks pleasing. So this is, I don't expect you to memorize this, but basically when they build a truss type bridge, these are going to be the various components. There'll be bracing to keep it from swaying to side and stuff like that. But our main load carrying element is going to be this kind of this orange area here. Question?
Is the purpose to increase the tensile strength of the bridge?
Well, it's kind of going that way. What we're going to be doing, and we'll see this when we start looking at bridges, simply supported bridges, what we'll see is that the bottom will be in tension and the top will be in compression. And this will be something you'll be doing when you get into mechanics materials, because we're going to see the same effect in beams too. And basically what it's doing is pushing the material out, so again, the material's we don't need as much material to carry it if we can carry it further away. But where I'm going with this particular question. Oh, where I'm going with this though is that when we look, there's bracing going across there that's going to be doing stuff for maintaining it against wind, possibly something from the stream hitting it or something like that. But the main load carrying thing here, you'll notice, is all in a plane. And what we're going to be doing in our next lecture here, basically, next couple of lectures here, is looking at these trusses. And what we're going to find is even though they're three-dimensional, we can analyze them in a two-dimensional sense here, because the main load-carrying portion, again, going back to it, is going to be this, that orange area there. Now, what we see here, and again, I don't expect you to, you're not going to have to memorize these, but everybody had ideas on how to create a truss. So they started off from very complicated ones like Fink ones to double intersection Warrens. But then there's also some nice simple ones like Pratt, Howe, and stuff like that, or the A trusses.
Mm-hmm. So are the planes or the forces are distributed, are they the same for the different types of bridges, like whether it's an arc bridge, an under truss, over truss, or do they change for different types of bridges? Does the plane change?
Does the plane change?
Yeah.
Yeah, I mean, you can, this is the main load carrying plane, but if we look at it sideways, transversely, there's going to be some truss elements that are going to resist the wind. But the nice thing is that's 90 degrees off. So again, we're going to be able to look at that in terms of a plane most of the time. Now there are three-dimensional trusses. Don't get me wrong, there'll be a lot of those. But generally, in terms of the load carrying capacity, it's going to be those two parallel sections there that we need to think about. Or if it's a roof truss, there'll be many of these, but basically the idea is those things are carrying the load. So where we're going is many trusses can be analyzed in two dimensions, so that's what we're going to be talking about. And the definition of what we're talking about then will be a plane truss, so it's not a boring truss, it's a plane truss, P-L-A-N-E. And it's basically the two key concepts that we need to think about this, and it'll make more sense when we start getting into the assumptions here. It's a framework of members joined at their ends. When we look back at all of these, there's nothing going on in between, right? I mean, they're all connected to other pieces there, but just at their ends. And that's going to give us the ability to do some assumptions along the way there. And then, of course, for us to be able to do it in this two-dimensional sense, it has to lie in that plane. I think that's the last one we have, yes. Okay. All right, you want to hit the lights there? Now that I got your attention. Okay, so now what we're going to do is talk about some of the assumptions that we're going to be needing to basically get ourselves into doing the analysis portion here. Continue a little bit Okay, the basic element to trusses is going to be the triangle. And again, as we said, they're connected at the ends. So our definition that they're connected at the ends, and they're pin connected at the ends. But the nice thing when you think about this particular truss, it meets our definition of a rigid body in the sense that it's not collapsible. If I push down on this, if I pull on this, if I go this way with it on one of these ends, those members basically, since they're all connected into this pin, what we have basically is a rigid structure. And then it meets our static definition of a rigid body, not the guy that works out in the gym, but the deformations of any of those pins when we push or down on it and that sort of thing are going to be small with respect to my little abbreviation there, WRT, with the dimensions of it. So when we think about that, this is going to be in feet or meters and that sort of thing. And when we consider the deformations there at those pins and stuff, we're probably talking less than an inch and maybe down into the millimeter stage there in terms of the SI system. So it meets our definition then of a rigid body. The problem is if we consider, say, for example, building our truss out of maybe 4 elements like so, well, consider the fact if I do some sort of a push along here, because those are pins there, they're not going to resist any sort of rotation there, and the structure is going to be able to move over like that. It can collapse, essentially. Now, everybody thinks that, and then anytime they see a four-sided thing, they say it's collapsible. Well, not all cases. You can have a case like so, and that's not going to collapse because those three of the corners are being held by something. Question?
What if you put two triangles together? Would that be possible?
Yes. Well, matter of fact, that's how we're going to build trusses, basically. Is it's just going to be a combination of trusses. We're just going to keep going like so, like that. Yeah. Think about it. It's another triangle, so it's rigid. They're connected together now, so when I pull on that, if this end's restrained, then it's not going to go anywhere. So good thought. Yes. That's how we're going to construct those, basically. We're going to follow through with that. Just a couple of other things, though, before we start building them. Okay, we have structures like this, and actually you'll see most bridges and that sort of thing are actually going to be composed of this. If they have more than 3 members, then we have a redundant system. And as engineers, that's what we like, because what that means the nice thing about redundant members, or redundant trusses, is that if one of the members fails, if just somebody cuts it or something like that, basically what we'll find is that it doesn't collapse. We just simply, if this one disappears, like so, well, what we've got is just simply 2 triangles hung together there, and away they go. They're fine. Now, the only problem with that is we can't use our statics equations to find out what's going on the inside. We can find out the forces on the supports that it's on, that sort of thing. So don't get me wrong there, but we can't go in and analyze necessarily all of the elements. Now, we like structures like this. An example of a structure that wasn't redundant was the I-35 bridge in Minneapolis, Minnesota that went down. That's what they call it. When you hear bridges described as fracture critical, basically that means it's a situation like this. If one of these members fractures, the whole thing goes. And that's what happened in Minnesota there. They had a situation where one of these gusset, all the gusset plates were actually designed a little bit smaller than they were supposed to be, half the size. And finally, one of them got tired and gave up the ghost, and then the whole structure came down. So that's why we tend to like redundant structures. Because if there are issues with the member getting overstressed and that sort of thing, or breaking, fracturing, or something like that, we can see it, the rest of the structure is holding up, and we can basically then maneuver to get it fixed, get people off of it, for one thing. So before we begin the analysis, what we're going to talk about are some of the assumptions we're going to make along the way there to be able to solve it. So there'll be 3 main assumptions. But there's 2 reasons to think about the assumptions. The assumptions will give us the ability to create tools then to analyze the structure. But it also then brings back to us, in terms of engineers, how realize that our particular analysis method is really getting us kind of ballpark figures. That's why I don't want significant digits out to 10 or something like that, because we're really not going to be close there when we consider some of these assumptions that we're going to make here. Well, it'll make sense here when we talk about the first one. To make our analysis go, what we're going to assume is that the members are connected by pins. Now, free to rotate, so there's no moment capacity there. We don't have a couple there of any sort. But when we think of some of those situations there are our actual situation. Think of the wood structure that we saw there with the metal plates and that sort of thing. The one case we saw in terms of the three-dimensional one there in the airport truly had a pin, but a lot of trusses will have this situation where they have a a gusset plate that is going to be basically holding the members together there. And it's either they're bolted in, such as wood. If they're metal, they might be welded in. How we're going to treat that is going to be this, with a pin connecting them all, allowing them to freely rotate. Now, a gusset plate doesn't allow free rotation, but it's not too bad, because when you consider the length of these members and how small that gusset plate is, by the time you get down here 20 feet away or something and you try to move it, you're going to be able to rotate it a little bit and that sort of thing. So the approximation isn't too bad. But again, note, in terms of solving it for real forces in the members and stuff like that, when you want to go to a finite element and stuff like that, you would model the gusset plate and that sort of thing. So there would be a little bit of rotational restraint there. But again, our analysis method, assuming pins, gets us close enough. It gives us ballpark figures so we know how to size the members. Okay, now as a result of that, we said that the members are connected at their ends. We've assumed now the ends are pins. So we got a member that looks like that, and that's how it's connected to anything else, right? What does that look like? Again, think about our free body diagram. If we take and substitute whatever it's connected to, say that one, it's connected to 3 members there and 2 members here or something like that. When we pull that member out and look at it, the only forces getting in there is going to be at the 2 ends. And the pin gives us how many forces? That's what I want to hear. What is that now? How many forces? 2. Do we know any tricks with 2-force members? Yeah, a couple. We should. We better. We're going to take that now, because our assumption 2 Oh, thank you. I'm getting so excited here about it. So this comes from assumption 1. Basically, now that we've assumed that those ends are pins, basically we can then go in and state that those members are going to be 2-force members. And recall our very special equilibrium that we talked about way back when. Since we assume that it's a 2-force member, how many unknowns do I have in this? If I know that this one's going to be equal, opposite, and collinear, 1 unknown. Yeah, that's a nice thing. So we only have 1 unknown in that particular piece. The other nice thing is since truss members are consistent of straight members, notice that the member follows the line of action there. which means then I can calculate the internal force in that particular member there, because I can cut that member and still have a two-force member. Where'd my red go? So since my member follows the line of action of the force, because again, the forces have to be going through each pin there. They have to line up per the pin. When I cut my member, the end force doesn't change because this whole member has to be in equilibrium. But when I cut my member, what I find then is then I can calculate an internal force of that member because it follows that line of action. And again, compression basically means that the member is being squished. And we can do the same thing with tension. And note then, what we're saying here is in terms of the internal force, it's the same as the external force. So if I can calculate the external force here at this point, at that pin, then I've calculated the internal force. So if I've calculated this as compression, it's going this way, squishing the element, then basically I've calculated my internal force of that member in compression. Same thing with tension. A special case that we don't necessarily see too often is the situation where we have the weight of the member. Now, we generally don't see it in a lot of problems because what we'll find is in terms of the weight of the member is so small compared to the forces it's carrying, generally we ignore it. In most problems it won't be there. But just, again, read the problem. If there's a weight in there, then you need to deal with it. Now, the problem is that our weight the weight's distributed over the element. So in our actual case, this is what it looks like. What we're going to do in the idealized case And what we're doing is just simply treating them as external loads. So if you do get a case like that, now this is assuming the member is straight and doesn't change dimension. If it changes dimension, well, then you end up going to your CG, trying to figure out the CG, and then distributing the weight that way. Again, very rare to happen, but just so you know that it does occasionally happen. Okay, so that's all of our assumptions. So now we get into solving problems here, which is going to be the fun part of the problem. And there's two different approaches. We'll talk about one today. And the first one is not to be confused with going out to local bars and that sort of thing. It's called the method of joints. And what we'll see is that this is really nothing more than something we've already done, particle equilibrium. And then the other approach that we'll talk about when you get back is method of sections, which now is going to be a rigid body. And with the rigid body, then we have the moment equation. Remember, in method of joints, since it's particle equilibrium, everything goes through that one point. And we don't have a moment equation available. So it's just going to be sum of forces x, sum of forces y. So we'll talk about joints today, and we'll solve some problems. Okay, so we'll talk about the process about going about solving this. So getting started, how are we going to get started? Couple approaches. One, let's find a joint with two unknowns. Now, why would I want to do that? Make me into one. Yeah. How many equations do I have available to me in particle equilibrium? Just two. Sum of forces x, sum of forces y. So if I have a joint with three unknowns, I can't solve anything at that particular point. I can't solve the three unknowns there. We may find a structure that doesn't have, we can't go out and find one. So another approach then we can solve for the reactions at the support. Again, our truss is going to be sitting on abutments or something like that, or pin and rollers and that sort of thing is what we'll see. So we're going to treat the entire truss as a free body diagram. We're going to basically not look at internally what's going on there. So we'll have a situation where you might have a truss like this, and you can't find, when we think about that, there's three unknowns there, there's three unknowns there, three unknowns there. Don't know how to deal with that. But the thing has to be on the ground. So what we're going to do, what we're suggesting here is then we treat this Like a free body diagram. Notice there's no internal members going on here. I'm talking, remember, the definition of a free body diagram is the external boundary. I don't care what's going on the inside. The only thing I care about in the inside is maybe weight. But those truss members I don't care about. But again, this truss is a rigid body. What I'm going to be able to do is just simply solve for the forces. And note that if I solve for the vertical force here, all of a sudden now I have a joint here that has two unknowns. Then I can get started. So our other approach then is once we solve this truss as a free body diagram, we have these reaction forces, then start at one of these joints here. Notice we have two forces that will be solved here. Again, there's only two unknowns there. So we can get started with our particle equilibrium. Now what we'll find is that it's basically a systematic approach. We're going to be just charging along here. Our first step So we're going to start off solving a joint with two unknowns, whether it's somewhere here or we actually have a joint hanging out in space there that we can start off that has two unknowns. The next step then in terms of the systematic approach Okay, then what we're going to do is once we've solved for the forces in these members here, again, since they're two force members, I know the force at the other end, equal, opposite, and collinear. So I can follow that up to the next joint there, say in this particular case to this one. If I solve for this known force here, then I come up to this joint here. I've got this one now member force, and then two unknown member forces. So now all of a sudden I've got two unknowns. I can use my equations of equilibrium there. So we're going to take what we've done, and then we're just going to kind of walk our way as we solve things, walk to the next set of members there, the next joints basically, following the members that we just solved. Okay, and then the other thing too is the other thing we can do with solving the whole truss as a support. Say, for example, we have a truss that we can start off with not having to solve for that. We can always go back and solve for the truss as a complete rigid body, get those reaction forces, and then go back and check the joints. So we got a reaction force here like of 500. Okay, well, does the vertical member there carry 500? If it's 400, then something might be wrong. So we can use the support forces to check ourselves too, to make sure that we've actually calculated it correctly. Okay, so we'll go to the handout now. So there's a lot of stuff there. Okay, so what we're doing is we're solving for this truss. So we're just going to be basically solving for the forces in those members. And again, as a designer and that sort of thing, you probably use method of statics to come up with sizing those members before you actually design them and throw them into a finite element program. Now, I wanted to show you the exploded view here, which I want to keep making a point here. This is not the free body diagram. This is showing you basically how the members and the joints react to each other. And it'll be basically the difference between method of sections and method of joints there too. So when we think about pulling those members away from those joints, okay, we'll think about, let's A here. Now just those particular FAY and FAX is just simply because there's a pin support there. And since there's a pin support there, I've got those two unknown quantities, one single force, but I've got an x and a y component there because I don't know its direction. When I think about pulling member AB away from it, so we shrunk it, but see how the member, we're assuming that particular member's in tension there. So when we think about what it's doing to the joint there, it's going to be pulling away from the joint. And then equal, opposite, and collinear force there, the member force is going to be pulling on the member itself. So you can kind of see how the tension of a member relates to the tension of a joint there. It's pulling on a joint there, and it's also going to be pulling on the joint there at B. Same thing with all the other ones there. We just shrink them basically. We assume that one's in tension, or this one in compression actually, I'm sorry. We're assuming it's in compression. Now again, the nice thing is with statics, sign will basically correct us. We know the direction. We can pick a direction, we can pick a sign. If it's the incorrect direction, basically signs will correct us. And we'll go through the problem solving it that way just to see how it goes. Again, we've got a roller support here. So the ground sees this, the ground's pushing back on our structure there, but it's pushing at that joint. So we're going to have a component of force at that joint there, and we're going to have a component of that force there from FAC, and then when we look at FAB, we're assuming that particular member's in compression also, squishing the member there. If it's doing that to that member, then it's going to be pushing down on that joint like so. And then finally, out here at B, we've got the known load of 84 kilonewtons. Again, it's acting at the joint, as are the two member forces there. And then there's some quick calculations since they didn't give you any particular angles. Again, when we think about this, what we're going to be doing now in our method of joints, we talked about it being particle equilibrium. What I'm going to be doing is looking at these particles. So these are the joints that I'll be looking at, knowing that if I solve for a force in this direction, pushing this way, then I solve for my member force. I know that that member has to be in compression by that same magnitude. If it happens to be pulling at the joint, I know that in my member then, the member will be pulling back basically because of Newton's third law there. I'll have a member in tension. And then these are, again, just a bunch of angles that are calculated there because they didn't give you any angles there. But again, when we think about this, what we're going to want to do is when we get into that joint equilibrium, we're going to want to solve forces in the x and the y direction, set them equal to 0, and then solve for those components. So our unknowns in this particular case here are going to be the three support forces there, and then the three member forces. And what we'll find is that's 6. We have 1, 2, 3 joints. Each of those joints has 2 equilibrium equations available to us, basically, so we'll be able to solve for all of them. Any questions before I hide this? Sure.
So the top member, that one's in compression, right? Because the forces are going outside?
This one here?
I know the top one that's kind of going at the angle. No, the member.
This one here.
Yeah. The member itself, that's in compression? Or?
That's in tension. It's pulling like a rubber band. See, think about how this is what the member sees. If you're pulling like this,
What the member sees? Okay.
yeah, And then what that joint or this joint's seeing is a force then pulling away from the joint. So that's
Okay, I'm seeing it backwards.
Okay.
I thought the joint was putting a force on the member, and the member is pushing back.
No, yeah. Think of it this way. This is what you're seeing in terms of the member.
Yeah.
Yeah. Now this is what you're seeing in terms of the joint.
Okay.
Think of it that way. Yeah.
I'm seeing the arrow.
Okay, you were looking the other way. Sure. I should have exploded my view even smaller, huh? Everybody comfortable with this before? Sir?
Could you explain how the member on the right is in compression?
This member?
Yeah.
Well, note, again, let's look at that member by itself. If the forces are pushing on it like that, right, it's squishing it, that's considered compression. You'll learn a lot more about this when we get into mechanics of materials. But think about what it does to the joint. Well, if it's doing this to this member, then it's got to be the equal and opposite direction on the joint. So what it's going to be doing is pushing at the joint. So if that member is truly in compression, what we're going to do is we're going to solve for a force then that says I'm pushing down on you. If it solves for it the other way, then it says the member is going to be in tension. We'll just flip signs.
So that is, in fact, in compression, then FAY has to point down, right?
Yeah, well, I purposely drew one wrong.
Well, I just want to make
Yeah.
sure I understand.
Yeah. You're thinking, you've already got equilibrium, you're solving equilibrium in your head. You recognize the fact that this member probably isn't right. But I always throw one in there just to show you that the sign will take care of it. And you need to recognize that. And that's why we've got to be very careful about putting in the signs. But you're thinking way ahead of me there, yes. You're thinking like a structural engineer. Any other questions? Sir?
Can you have it where part of the member is in compression and part of the member is in tension, or is it always going to be like?
In this analysis, now, if you get into, finite elements and stuff, there's going to be bending and stuff like that where portions of the member might be in tension and portions of the member might be in compression and stuff like that. But in this particular analysis, since we've assumed the members are two force elements, we're just basically going to assume it's the same force throughout. I'll save the other cool stuff for mechanics and materials. Any other questions? Okay, so what we're going to do is we're going to go ahead and solve that problem via the method of joints. And what we're going to see is that, again, it's systematic, but it's the same thing that we've been doing. It's just simply going to be draw the free body diagram, or you'll lose points, and then apply your equilibrium equations. Same thing that we've been doing in two-dimensional equilibrium. Okay, now we'll note in our problem there when we look at that, joint B, how many unknowns are there at joint B? We've got one known force at 84 kilonewtons, and then we got two members attached to it, two unknowns. So that's going to be one of those problems. It's going to be real nice that we're going to be able to start at B. So our free body diagram looks like this. It's a very hard one if you don't get the circle quite correct. And then we're going to choose a coordinate system. Again, it doesn't have to be horizontal and vertical. You can rotate it to the member. Just make sure you get your angles in there correctly. And we put in our known loads. Which is vertical, 84 kilonewtons. And then according to the picture that I drew there, will be FAB, FBC. So I put in my forces, and I just choose arbitrary directions. I choose arbitrary signs. The directions are actually defined. So they're going to be pin to pin, basically like that. So the direction's defined. That's why there's only one unknown in there. But I'm going to choose my sense. It'll either be that way, compression or tension. And then the other thing I need is my dimensions. Well, nice thing about point equilibrium or particle equilibrium, what I need is angles. Okay, so then my next step is setting up the equilibrium equation. So I just simply take sum of forces x, sum of forces y. And the x direction is pretty simple, although it contains two unknowns. But again, pay attention to the signs. You've chosen a direction now, so when you start plugging things into your sum of forces x, sum of forces y, you've got to apply them in the correct sense there. So the a is going to be positive, the bc portion is going to be negative per what I've drawn those arrows. And then when I get done, I'll be ready for substitution because I'll have FAB in terms of FBC. So straightforward calculation there. And again, I'll set up my next equation, choose a positive direction. In this case, I'll choose it with the positive y. And I know that my 84 is acting in the negative direction, so I'm just going to shove that over to the other side of the equation there, which makes it positive. I substitute that into that. I'm able to solve for FBC as 80 kilonewtons. Now remember, in two-dimensional equilibrium, or any equilibrium, force is defined in terms of magnitude and direction. Well, we kind of know the direction here. What we're going to be asking for you in the truss analysis is that member in compression, or this member, sorry, is this member in compression or tension, based upon the way I solved it. So it came out as a positive quantity, right? So that means my arrow's in the right direction, right? So what is it doing to the joint? It's pushing on it. So what's it going to be doing to the member? In reverse, it's going to be pushing back. So we'll report that then as compression. And then going through my substitution, I can shove that back into there. And it comes out with a positive quantity. What is that member doing then? It's the opposite. It's got to be in tension. It's pulling on my joint. So it's pulling on my joint. When we think about the member out here, it's going to be pulling back.
Can you say that one more time? Why is it tension?
Okay, well, first of all, going back just to my equilibrium, I solve for it as a positive quantity, which means my arrow is going in the right direction, right? Okay, so when I think about my member out here, to be in equilibrium, it's got to be pulling that way. So the member's seeing tension, and what the joint is seeing is then a tension. It's pulling from the joint. So arrows going away, basically, from a joint is going to be tension.
Okay.
And arrows pushing into it, basically, are going to be in compression. But it's a good thing to keep in mind. That's one thing that you always tend to forget about, those little pieces like that. Okay, so following our systematic approach, we solved a joint with two unknowns. Now we've got two forces that I can follow there, AB and BC. So my step 2 is follow that known member force, because I know what the other end of that force is going to be there, to the next joint. So we'll follow FAB. What are we doing on time here? So again, that very complicated free body diagram there. Okay, so I solve for it as 52 kilonewtons. And I know, again, when we follow that member, notice that it's pulling at this joint. So it's going to be pulling at this joint too, if the member, again, is in tension. So make sure that when you start bringing those arrows, this arrow will be pulling, this arrow will be pulling if the member's in tension. The only problem is, oops. Is that AC? When I go to that joint, the problem is I've got 3 unknowns there. And the part of it, the main reason is because I've got a pin there. It's connected to the ground via a pin. So when I connect it to the ground, it's an unknown force and an unknown angle. Hence, I express it in terms of x and y components there. 2 unknown components, but I also have this extra member force here. So I can't go there. What I'll do then is just simply go back to my next member that I had solved. In this one, I'm going to follow BC down the line. Everybody got this before I erase it? Question?
Why can't you find the FAX? Or
You're right. You probably could find, yeah, because it has to be equal to the vertical component there. So you could get a piece of it, but you're not going to solve the whole thing. So you can get that portion, yeah. But again, what we'll find is generally, everybody got this?
You want to do the joints or the pins last.
No, we just simply want to follow it to another joint. So we're going to follow this one. We solve for 2 forces here. I get my choice of which way I want to go. I'll go to BC. And this is something when you start solving them, you're just going to look at it and go, this is where I want to go. So we'll find when we look at joint C, and again, note that we solve this as compression, so it's pushing on that joint. When I look at the other end there, it'll be pushing on that joint. And then the other 2 forces there are going to be the AC component. And the one thing that a lot of people tend to forget, and I'll see this a lot in joint analysis, is they'll forget about the support. When we look at that, the support there as at C is going to be providing a horizontal component there. It's providing force of that joint. A lot of people tend to forget this piece. So you're not going to forget it. We're going to hit it into you. So when you get to places where there are supports, and this is the nice thing, when we talked about that 3rd step, you can check it. You can solve for the support forces of the entire truss. And did you get the same result as you did through the joints method? So it's another nice check there.
Is it because the compression is pushing back on that?
Yes, it'll be pushing. Now again, thinking about we can get that vertical or the horizontal equilibrium right away, because the horizontal component of this force has to be equal to the horizontal component of this force. So what we'll find, it's a very easy calculation there. What is that, 36.87? Did that answer your question? So our equilibrium equations, probably the first one we would want to solve, and good suggestion by the young fellow there, realizing the fact that I can set up one equation, one unknown there. And what my equation will look like then is the horizontal component of that. Is it okay using a sign for that? Okay. Again, be careful where those angles are measured from too. That's the other thing that they'll try to catch on in various exams. But F Cx will then equal, now since it's a support force, I can't report that as compression or tension, so I actually have to report a direction. And since I know it's horizontal, it's going to be pretty easy there. But again, this is a vector. We need to report it as a vector. And then the other piece then, and this is why I say pay attention to your signs. FAC is going to be negative. FBC is also negative, and cosine of that angle. Oops. So what that equation will look like is two negatives. So I've drawn it in the wrong direction. What I realize then is that the sign will correct me. So don't worry about that. As a matter of fact, when we get into method of sections and when you go into structural analysis courses for you civils and stuff like that, what you're going to be doing is table methods, and we'll assume all tension is positive and all compression is negative, and it provides nice ways of calculating there. But this is just simply our two-dimensional equilibrium. We're assuming a direction, come out negative. The direction's fine, it's the sense that's wrong, so we just simply flip it over. Now the key thing, though, is when I'm going to follow that, I need to make sure that I now show that as tension. So when I take it up now to joint A, and the only thing really at this particular point in time, I may not even want to go here, because if I've been asked to solve for the member forces, I really don't even need to go to A because I've already solved all three member forces. But again, you want to check yourself, just make sure your calculations are correct, and we can check that against, oops, yeah. So again, a proper free body diagram is going to have not only our forces, but then our dimensions, in this particular case, 58. The angles, everything else is pretty perpendicular angles like so. And we can solve for the horizontal or the vertical component of that support force at A is 84 kilonewtons up. No, that's 67, right? Put that over there, yeah, 67. And I can solve for then the other component of my support force. Okay, and then, almost over, we can solve for what we can do now to check ourselves. We just solved for our support forces there. We can solve for the whole truss without looking at the internal members now. Again, my free body diagram is the external boundary. All I care about is the external forces now, so there's no internal forces here. I'm going to check that against just simply looking at the truss as a free body diagram. We look at that free body diagram. Now, since we've got a free body diagram with some distances and stuff like that, and forces that we're going to have to take out of place and that sort of thing, take out of their lines of action, we've got moment equations available. So we'll take moments at A there. It's got two unknowns. We've got the 84 at 3 meters. And what we find then is just simply solving for that support force. We find that is 48, which when we go back to look at our joint C, that was 48. So we've checked it two separate ways now. We went through method of joints where we were just simply walking our way through. And then we also have this ability to solve for it. The truss has to be on some sort of a structure, basically. We can solve for the support forces separately, check against what we solved for in the method of joints, and away we go. Any questions? Okay, quick. I heard books closing. A couple of quick points here. We may cover a little bit on Thursday when we get back to. But this will make life simple. Everything's special. Things that make the first case we'll look at is where you have two members connected, and you only have two members connected. Now, I mentioned here that I've got two members / forces. Again, the way to think about these special cases is think about these members. When we think about these members acting on a joint, this is what it looks like. This is my free body diagram of that particular joint. Now, if I consider equilibrium, and I haven't drawn my coordinate system there, but when I consider, in this particular case, doing vertical equilibrium at that joint there, this is the equation I get. So what does that tell me? How do I make it? If it's an equilibrium, it's got to be equal to 0. So there's two choices I have here: is my angle or my force. So if it's constructed at an angle, I can go measure it and that sort of thing. That implies then that force is 0. This is known, you'll see this all the place, 0. Matter of fact, you'll probably have a homework problem next time on this. It's the 0 force members. So the nice thing about finding a situation like that, when you go there, if this member is 0 here, if we just assume that F2 is 0, then at the other end, there may be 2 other members there. If that's 0, I can go to this joint now, and I have 2 unknowns because this member is equal to 0. And I don't need to worry about calculating it. Same thing with this one. I can follow it along. And basically, it's got to be 0 at the other end. If it's 0 at this end, basically, it has to be 0 at the other end. Now, the reason why I bring up thinking about this in terms of forces is a lot of people will see something like this. Are those 0 force members there? No, there's 3 forces. When we consider the free body diagram, it looks like that. So you got to be a little careful with it. It's not 2 members per se. If there's forces hanging on it and that sort of thing, when you get to that equilibrium problem, you realize basically I don't have 0 force members here. When I look at this situation, think about it in terms of forces. Basically, it says, well, if they're out of line. Now, the one case, we're down to the wire. Now, you wouldn't really see this because this would buckle unless the member's in tension. And actually, well, yeah, actually would. There's suspension structures that are like this. Again, think about this in terms of, well, actually, it would never be in compression. Are those 0 force members? No. See, that's F1, that's F2, but it's a 2 force member. So basically, whatever F1 is, F2's got to be. So there is the one exception. When alpha is equal to 0, we have the situation where, and you'll see this on, basically there's suspension structures where they, instead of a wire, they use the rods. And they'll have basically the rods lined up and pin connected, because again, they didn't form them as real long members and stuff like we do with the cables and stuff. And you'll have that situation there where you've got the members like that. All right, have a good break. We'll see you guys on Thursday.